CUDA cores. These are the general-purpose workers inside an NVIDIA GPU, and the rough equivalent on other brands would be shader cores or stream processors. They handle the basic math behind graphics and many compute tasks, including lighting, geometry, effects, and parallel workloads. More cores usually means more raw throughput, but core count alone never tells the full story because clock speed, architecture, cache, and memory bandwidth all matter too. They matter because they are the foundation everything else builds on. Clock speed. Clock speed is how fast the GPU's cores run, usually measured in megahertz or gigahertz. A higher clock means each core can perform more work every second, at least in theory. Boost clocks are especially important because modern GPUs automatically raise speeds when power and temperature allow it. This feature matters because even a GPU with fewer cores can sometimes compete well if those cores are more efficient and run at higher sustained speeds. It is one of the clearest examples of how GPU performance is not just about size, but also about pace. VRAM is the dedicated video memory a GPU uses to store textures, frame data, geometry, shaders, and other assets needed right now. Unlike system RAM, it sits directly beside the graphics processor and is built for very fast access. More VRAM helps with higher resolutions, larger texture packs, complex 3D scenes, and certain creative workloads like video editing or AI models. It matters because once a game or application runs out of VRAM, performance can drop sharply as data spills over into slower system memory. Memory bus. The memory bus is the pathway that connects the GPU to its VRAM, and its width is measured in bits, like 128-bit, 192-bit, or 256-bit. A wider bus lets more data move at once, which can dramatically affect how quickly the GPU feeds its cores. On its own, bus width is not everything, but together with memory speed it determines total memory bandwidth. This matters because even a powerful GPU core can be held back if it cannot get data quickly enough from memory. Memory bandwidth. Memory bandwidth is the total amount of data the GPU can move between the processor and VRAM every second. It comes from a combination of memory speed and memory bus width. High bandwidth helps in situations with large textures, high resolutions, ray tracing, and other workloads that constantly move huge amounts of data. It matters because graphics performance is often limited not by how much a GPU can calculate, but by how fast it can be fed. In many real workloads, bandwidth is what separates smooth performance from constant bottlenecks. Cache. Cache is a small, extremely fast layer of memory inside the GPU that stores frequently used data closer to the cores. Modern GPUs use bigger and smarter caches to reduce how often they need to reach out to slower VRAM. That can improve efficiency, lower memory pressure, and sometimes let a card with a narrower memory bus perform better than expected. It matters because cache quietly boosts performance behind the scenes, especially in repeated workloads where the same data gets reused again and again. Ray tracing cores. Ray tracing cores are specialized units built to accelerate realistic lighting calculations, especially the tracing of rays as they bounce around a scene. Instead of faking reflections, shadows, and global illumination with older shortcuts, these cores help simulate how light behaves more naturally. The result can look much more convincing, with better reflections on glass, more accurate shadows, and richer lighting. They matter because they push graphics closer to film-style realism, though they also demand a lot of performance and usually work best with other features that help recover frame rate. Tensor cores. Tensor cores are specialized units designed for matrix math, which is heavily used in AI and machine learning. In gaming, they are best known for powering features like AI upscaling and frame generation, while in professional work they help with training and inference tasks. Their main advantage is speed, because they can process certain types of calculations far more efficiently than standard shader cores. They matter because modern GPUs are no longer just drawing images. They are increasingly built to predict, enhance, and reconstruct them with AI assistance. Upscaling. Upscaling is a feature that renders a game internally at a lower resolution and then reconstructs it to look like a higher one. Different versions use spatial methods, temporal data, or AI models, but the goal is always the same: gain performance without losing too much image quality. This allows demanding games to run faster, especially when ray tracing is enabled. It matters because it has become one of the most important modern GPU features, turning previously unplayable settings into something that actually feels smooth on mainstream hardware. Frame generation. Frame generation creates additional frames between traditionally rendered ones, usually by analyzing motion and previous frame data. Instead of the GPU drawing every single frame the normal way, it can insert AI-generated or algorithmically generated frames to raise perceived smoothness. This can make motion look much faster on screen, though it may also introduce artifacts or affect responsiveness depending on the implementation. It matters because it represents a major shift in how performance is delivered, not just by brute force rendering, but by intelligently filling in the gaps. Encoder and decoder. These are dedicated media engines inside the GPU used for handling video compression and playback. The encoder helps create video streams for recording, streaming, or exporting, while the decoder helps play back compressed formats efficiently without loading the main GPU cores as heavily. Better encoders mean cleaner live streams, faster exports, and improved support for modern codecs. They matter because a GPU today is not just for games. For creators, streamers, editors, and even everyday users watching high-resolution video, media hardware can be just as important as raw gaming performance. PCI interface. The PCI interface is the connection between the GPU and the rest of the computer through the motherboard. It determines how much data can move back and forth between the card and the system, with newer generations offering more bandwidth. In most gaming situations, this is not the main bottleneck, but it can matter for lower lane cards, professional workloads, large data transfers, and certain storage to GPU use cases. It matters because the GPU does not work alone. Its speed also depends on how well it communicates with the rest of the machine. Power and cooling. Power delivery and cooling are not flashy features, but they shape how well every other feature performs. A GPU can only maintain high boost clocks and stable operation if it has enough power and can keep temperatures under control. Better coolers reduce thermal throttling, while stronger power designs help the card sustain performance during long workloads. This matters because advertised specs mean very little if the card cannot hold them. In practice, stable performance over time is often what separates a great GPU from one that only looks impressive on paper.